Very excited to welcome you and introduce our speaker, Saurabh. He's going to be talking about optimizing AI and ML workloads, resource management, and cost attribution. Thank you very much.
Awesome. Thank you for the introduction. Hello, everyone. My name is Saurabh. I am an engineer at Outer Bounds. And today we are going to be talking about optimizing AI/ML workloads with a focus on resource management and cost attribution. So on my flight here, all the way last evening, in the morning today, I was like, this is a pretty long topic name. Like, what does this even mean? And I was on the phone with my dad, and he sort of asked me, what does this really mean? And I was like, you know what? At the end of the day, you can boil this down to two words: cost versus value. So the cost versus value, when you look at it from the prism of AI, there is this massive shift where every single enterprise company wants to build AI applications and is willing to spend a whole bunch of money in order to build that. Earlier today, I read a headline where it said Meta plans to spend at least $600 billion on infrastructure by 2028. Whether you speak to people on who are in university or in industry, everyone sort of agrees that AI is going to be a great tool. It's going to be an immensely amazing tool for productivity enhancement. Or you dig into every industry, and you'll find AI changing the nature of work. However, there is a dilemma. For folks who don't have $600 billion, GPUs are the currency of the world, but they're super duper expensive. You could potentially build out your own GPU farm, but again, you don't have $600 billion. So you're willing to trade large upfront costs for granular OpEx by renting GPUs by the second. The idea sounds relatively simple to grok, and we also sort of agree that AI/ML systems can produce a lot of value. There is no doubt, at least on that front, talking about truth. One of the truths that we just sort of heard in the last talk, that is a truth I think all of us can agree on. But there are a lot of questions that arise when you sort of say, OK, I want to use GPUs, and I want to build AI/ML systems. What kind of compute is the right fit for you? Like, small costs often add up uncontrollably if you're renting GPUs by the second. And how do you limit the usage of GPUs when you have multiple teams who are engaged in many projects that they want to execute on? Do you set like blanket limits where you say, oh, team A, you only get $100 worth of GPUs per day, but team B can only get $55, and you cannot exceed that quota? Now, what that ends up doing is, yes, you have put a very hard limit in terms of budget, but you're sort of spending a lot more money on human cost, where somebody has to stay up overnight and say, like, oh, I'm going to get $100 extra as soon as the clock ticks over the next day. So, and then I'll be able to get my work done. What about cost transparency? How do you know the workload that you ran, how much money did that workload actually end up eating into your budget? Coming back to GPUs are expensive. If you look at AWS offerings for GPUs, there are about 40 different GPU instance types that span across 10 different GPU microarchitectures. If you take a G2 8XL, you could choose that runs the K520 architecture. It can provide you up to 5.2 teraflops if you use all the GPUs, which it has 4 GPUs, you'll spend about $2.6 an hour with an on-demand instance. But if you take a G4 DN 8XL, with a single GPU, you can get 8.1 teraflops for $2.17 an hour. And that is about 20% cheaper. So which one do you use? Even if you knew which one you used, it is really hard to know if the cost that you are incurring in order to build these applications, is it commensurate with the value that has been produced? So let's look at a tool that will allow you to put in perspective what workloads that you have been running and how you can put the value that has been produced by these workloads into perspective. So what is Metaflow? Metaflow is a human-friendly Python library that allows data scientists to develop, deploy, and operate data science, AI, and ML applications. If you look at the picture up there, it is built on top of 6 principles, which we feel are the core to making any data scientist and computer administrator happy when working on data science, AI, or ML applications. A data scientist, for the most part, does not really care about infrastructure. They think about infrastructure as most of us think about electricity. It's a magical thing that just appears in a room when you flip a switch on. On the infrastructure side, though, the person in the yellow hat is often like, I don't really know how much workload is going to come in once I set up this cluster that has 500 node groups, and each node group can scale up to 5,000 nodes or whatnot. Metaflow also allows you to use production-grade deployments like Argo workflows in order to set up things like scheduled workflows or batch workloads. But most importantly, it allows for data scientists to use whatever packages that they want to use in creating their flows that will eventually result in well-trained models or AI and agentic AI or ML applications. So let's sort of see how Metaflow helps with this particular situation. Now, assume the jobs that need to get done are, there are interactive workloads, there are scheduled workloads, there are distributed training workloads, pre-post training, inference, or agentic applications. If you were to consider the stick figure as a data scientist who's written up a DAG, which essentially what Metaflow allows you to do, using simple constructs as decorators. Now you've written that code on your local machine. You've tested it out with a simple enough toy data set on your local machine. But now you're like, hey, I want to use this. I want to run my code against this massive data set that is sitting somewhere in S3 or in Azure Blob Storage, and I want to deploy my code to the cloud. Do I have to build the entire pipeline or the entire infrastructure to move my code from my local machine over to the cloud? The answer is, you guessed it, no. With Metaflow, you can use very simple constructs like Python flow.py run and append it with -- with Kubernetes, and magically your code will move from your local machine over to the cloud, whether the cloud is GKE, Azure, EKS, or any of your neo clouds that you might have worked with, Nebius, CoreWeave, you name it. So there is one framework that will allow you to build them all. Develop locally, verify and debug, and then effortlessly productionize using -- with Kubernetes on the cloud of your choice. However, fun fact, the cloud is neither free nor infinite. So now let's sort of dive into our original motto of cost versus, let's dig a little more deeper into cost versus value produced. We sort of settled on a couple of truths. We settled on the fact that AI applications can produce a lot of value, and we've settled on the fact that GPUs are super expensive, even if you were to rent them by the second. So we have to optimize the workloads that are running on these GPUs. A lot of times we hear from data scientists who are like, hey, yesterday my workload ran for 25 minutes, but today it took 5 hours. And the compute admin is like, I gave you all the compute in the world, then what is happening? There could be one or multiple of the following issues that you could see in your cloud cluster. The resource requirements that any compute admin might have envisioned, you've already blown past that. So the resources that you have available in your cluster are not enough. You have maximized your resource utilization for compute that is already present in your cluster. You might have minimized your resource contention. You think you have, but there are multiple workloads that are already gunning for the same resources. And the minimization of cost reruns due to flaky failures is sort of something that eventually eats up into the budgetary constraints for most teams, or you might not have optimized your cloud spend. So let us see what we can do for each of these categories. How do you predict resource requirements? Of course, it all starts with a conversation where our data scientists say, hey, we want to run 15 training jobs this quarter, and guess what? We also need eight H100s each. And the compute admin goes, bam. Yeah, I'm gonna steal that from a talk earlier today. The compute admin is like, okay, I hear you guys, but I have so much capacity available already. Are those node groups even scaling quickly enough? Like, you guys are telling me that you need all of this capacity and you demand all of this capacity, but I have stuff already configured for you. And I'm like, are these node groups scaling quickly, or are those node groups sufficiently bin packed? When you submit a workload, are those even getting scheduled on the right nodes? Are there noisy neighbors? What if there was a workload that was running on, there are two workloads that are running on the same node and are causing, and are sort of eating up resources on the node, which is causing one of the workloads to fail. Are the workloads right-sized? And the biggest trade-off, the speed of execution versus bin packing. So if you look at this graph, as an admin, or even as a data scientist, if you look at this graph where we are mapping the cluster demand, which is essentially saying how much of CPU or how much of memory is being asked for across time, what you can see is that the compute and memory is almost maxed out at 90%, and on a single day, it had reached almost up to 500%, which is memory. So if the workloads that you're submitting into your cluster are already demanding 500%, there is very little room for any other workloads to enter your cluster. On the other side, if you look at the workloads that are attempting to enter your cluster, given the fact that your memory demand is already 500% of what you have, there is a whole bunch of workloads in the lines in yellow that are actually just waiting in order to get scheduled, which is not good. So now as a compute admin, you look at this graphs and you're like, okay, maybe I need to add more compute power into my cluster in order to make sure that these workloads run with minimal time. Another axis that you need to consider is how do you maximize your resource utilization in a near real-time. What is a near real-time view that would help you to maximize your resource utilization? So let's say you've submitted a workload into your cluster, and you see we have a red line, which is sort of limiting the amount of CPU that workload can pretty much utilize at, let's say, 4 vCPUs. And this allows you to make sure that no single task can take over all the vCPU that is present on your compute. On the other hand, when you look at memory, because you've put in a guardrail for, let's say, 15 gigabytes of memory, your task has run out. And you're like, yikes, I've spent a lot of time trying to run my task on this particular compute, and now I'm stuck with an But while you get that feedback in real time, there is also an interesting conversation to be had to say, how can I optimize my tasks over time? Like, what has this task been doing? I've been running this task for the last 6 months, and how has this been behaving over time from the perspective of resource utilization? So if you look at this graph, on the x-axis we have time, time that has been spent since the task has started, since every execution of the task has started, and on the y-axis we have how much resource is being requested by that particular task. So on the left-hand side, on the purple graph, you see that as soon as your task starts, the density of utilization of CPU is very, very high, and you are sort of requesting about 3.7. You're sort of requesting about 5 CPUs, but you're sort of using almost, let's say, on an average between, say, 2.5 CPUs very, very heavily, but you sort of break, you sort of burst through, and you eventually end up using a maximum of 3.7 CPU. which sort of says that there is a little bit of waste in the amount of compute that you are requesting for, but not sort of utilizing. On the other hand, if you look at the graph on the green on the right-hand side, which is memory, you are sort of requesting about 75 gigs of memory, but you end up using 60 gigs of memory, which means between one CPU, vCPU, and 15 gigs of memory, you've pretty much spent about, let's say, $1 an hour that you could have reclaimed in order to use you could have utilized them better by giving them to some other workload. Another big issue that we see a lot of times is resource contention. So now assume that you had a single node which advertises capacity with 4 vCPUs and 64 gigs of memory, which is this thing in the middle. Now the first workload comes in and says, hey, give me 4 vCPUs and 60 gigs of memory, and it enters the running phase. But now there are 2 other pods which are asking for exactly the same resource, but hey, because you have ended up exhausting all the resources that are available on that particular compute node, the other 2 workloads are waiting. And remember, you had data scientists asking the compute admin, why did my task take 2 hours to execute today when it took only 25 minutes yesterday? It's entirely possible that the pod that is currently running on the compute node was not around yesterday, which is why the other pods were able to schedule themselves. Another view that allows you to quickly get that information is if you try to map on the x-axis we have time, and on the y-axis we have the number of nodes that are coming up over time. And looking at this particular graph, you can see that there's increased node demand in a time window, which can cause compute contention. If you look at around 11 a.m., there's actually between 2 p.m. and 3 p.m., there's a huge spike in the number of nodes that were spun up for, let's say, the M52X large instance type. Which can indicate that if there's another team that is also trying to get compute capacity from those nodes, they might have to wait, and that causes increased time when it comes to execution for their workloads. If you also want to look at it from the resource demand perspective, so we've seen how it looks like from the nodes, from the compute angle perspective. If you want to look at it from the resource demand perspective, you can see that across different node groups, which resources have maxed out their demand. So on this side, you can see that from memory, the demand is about 40%. So it sort of seems like you don't really need to add a lot more compute at the moment. The nodes are sort of coming up, but the demand from the workloads perspective for resources has not yet reached 100%. If it had reached 100%, you definitely have resource contention, as we sort of saw in a couple of slides earlier. So how do you sort of fix this? How do you sort of fix this issue? Now, a lot of times when data scientists are iterating on their work locally, they don't really need a lot of heavy compute pools in order to finish their work. So one strategy that can be applied here is to separate out compute pools for rapid experimentation and heavy lifting. So you can have a dev compute pool which can, let's say, only scale up to, let's say, 5 nodes, but your production compute pool can scale up to, let's say, 500 nodes. And you can write up your DAGs or your Metaflow flows quite easily locally and test them against a toy subset of your data on the given on the dev compute pool. And once you're done, you can push them up to production and optimize them for and target the heavy lifting compute pool, which are sort of optimized for steady state and high latency workloads. I think a lot of data scientists here might resonate with the fact that they run their workloads, and those workloads fail. It's a fact of life that if your code runs the first time, there's something probably wrong with it. So you've submitted code to production, code runs once, but then it magically fails because of either flaky failures or I/O or some other issues got introduced into the executing environment. And then your code has run for, let's say, 4 hours, and now it has failed. Remember, GPUs are expensive. If you have to start all over from time t from epoch 0, you have sort of thrown away money without getting any value from the work that was already done. So how do you minimize this rerun cost? Metaflow comes with 2 very simple to use decorators called retry and checkpoint. So let's say in this case, there was a process S3 step that was doing some data fetching from S3, and that failed because the node just went away for whatever reason. You can just do a retry, and Metaflow will initiate a retry of the failed step automatically without you having to ever get into the system and figure out why your run failed. And checkpoint, so now let's say you're doing a training flow, and as I said, your training flow has run for 4 hours and then eventually failed because, hey, the infra was balked for whatever reason. As you go along in your training step, you can use checkpoint.save, and it will save the current state of your workload into as flat files on disk. And even if you were to restart at a later point in time, it will restart from the latest saved checkpoint, so that you don't have to restart all the way from epoch equal to 0. Coming to optimizing of cost spent, remember we said that how do I choose which particular GPU is the best one for the workloads that I want to run? It is very, very easy to overpay for instances that your workloads cannot even fully utilize. So on the left-hand side, we have a G52XL, which costs you about $1.21 for an hour. And on the right-hand side, you have P38XL, which costs about $12.24 for an hour. But if you see, you're sort of getting the same output. But on the right-hand side, there are a ton of wasted resources, which means that eventually you're sort of just paying a lot more and you're getting the same work done. So it is imperative that there is some sort of research, that you do some sort of work before you pick up a particular instance type to where your workload needs to run on. Another trade-off when you talk about optimizing cloud spend is speed of experimentation or lowest infra. Now, a lot of times you just want, like, hey, my work is ready. I need to push this to production. So let me just I don't really care if the infra just keeps running all the time, and I just want lowest time of execution. So I'm willing to throw away some extra money. So I'm optimizing for speed, which means you're sort of going to downscale your compute a little more lazily compared to the other option on the top, which is you can optimize for cost, where you're like, I'm going to aggressively downscale my compute so that I don't spend any money. However, as I said, cost is not only infra cost. There is cost that is associated with human time as well. Because let's say if you go with approach 1, where you're optimizing for eager downscaling, you submitted a workload. Now, it is entirely possible that the cloud provider does not have the available GPU nodes available at the time when you're attempting to submit your workload, or you got only, let's say, you wanted 5 GPUs and only 2 nodes came up, which can give you a cumulative of, let's say, 2 GPUs. So your workloads are going to get stuck at that point. So there isn't a right or wrong answer to this. It's a trade-off of what you want to optimize for. Lastly, but not the least, cost attribution. If you've sort of we sort of started out by saying we want to. There's a trade-off between cost and value. When we talk about cost, we want to know, hey, I'm investing $600 billion into this particular project. So where is this money going? I don't want to spend $1 million on a project that generate, let's say, only $100,000 in incremental revenue, or where is the allocated money that I gave you being spent? Which team is using this money for what project? How do you surface that information to leadership or even to other team members or other teams who are working on different parts of the same project. Which projects have maximum ROI? And granular tracking of cloud spend from team budgets. These are all questions that most teams ask of their data scientists on most infrastructure and budgetary planning commissions ask their data scientists on pretty much on a daily basis. So you can monitor a lot of things from Metaflow, and we'll sort of talk about how we can do that. But as you can see, the AI ML flow spend over the last 30 days in this particular graph, there was a DeepSeek training flow that took, let's say, $6,000. But other ETL or event processing flow types, they did not really cause a lot of spend on their particular workloads. Or if you wanted to map out things based on the teams that were using cloud infra, you can do that as well. So how do you create these things? Like cost attribution demands data. So monitor everything. Now, and what do I mean by monitor everything? For effective cost attribution, you can monitor every workload or node or any part of your infra at different granular levels. Over here, I have an example for nodes and pods, or even CADvisor metrics, which can allow you very deep granularity when it comes to CPU usage or memory usage of your particular containers. So let's sort of kind of see how an example of how this might look in your particular cluster. So on the right-hand side, we have a bunch of nodes that have been executing in your cluster. You can always bring them up with agents, monitoring agents that will be picking up metrics like cube state metrics. You can have like node info, node labels, node annotations. I feel node labels and annotations are node labels, in fact, are quite important in this particular scenario because you can add any custom node labels that you might then use in your FinOps. These labels, whether they are on nodes or whether they are on pods, can be sucked in by tools like kube state metrics, which can then be stored in your overall monitoring servers. Let's say I've taken the example of Victoria metrics. Oops. I've taken the example of Victoria metrics here, and then you can use your monitoring servers to figure out or fish out queries that will give you the answer to things like, how do you do cost attribution based on a particular flow or based on a particular team? So the one thing I will leave you with is monitor everything. That's it for my talk. Happy to take questions. Yeah.
Hey there. Generally kind of asking around some of my data scientists when they're experimenting with the new model that they're working on, they sometimes have an issue with transitioning from their local environments for where they're testing or their staging environment to production and understanding what that infrastructure and compute needs to be in between, where we end up over provisioning a lot for that production because of the unexpected nature of what might happen. Are there any kind of good recommendations that you have around pre-prod investigations that we should be doing against our models to best assess that right sizing when we're moving to prod?
Yeah, great question. So there are two things that I've seen people do in that space. As you said, they'll always overestimate. One of the reasons for that is the shape of the data that your workloads might be executing on can change on a day-to-day basis. Like on one day, you got this massive dump of Parquet files, which let's say 5 terabytes of Parquet files that you had not accounted for. That can cause your workloads to Right now, you can imagine, like, you can be conservative and you can say, hey, listen, to start off with, I'm okay with the fact that my workloads are going to and if they do, then I'm going to figure out what I want to do with it. Or you can say, no, I really don't want this workload to or to fail for any reason, so I'm massively going to over-provision my workload. So it's a trade-off. right? The second thing that I've seen people do is utilize a view like this, where they will look at how much they have been provisioning or requesting from the cluster for how many resources they've been requesting and how many they've been using. Let's say you get that information for a quarter or 2 quarters or a month or 2 months, like whatever that timeline you decide to be, then you can start adjusting resources for your particular workload. So then you're like, okay, no, now I can sort of start lowering the number of the resources that I'd originally started out with. So there's always a push and pull in that direction. Another strategy could be you're going to use up the entire resources that are available on a cluster, but then you're going to limit the number of nodes that can come up for any particular node group. So you can say, oh, instead of this node group scaling to 100 nodes, I'm going to restrict it to scale to 20 nodes or 5 nodes. So there are different levers and different knobs that you can pull to sort of achieve that. But again, as I said, there is always this. Some interesting things that you can also do is if you have good relations with the other team, then you can borrow that compute from them, because generally compute is not sliced it's not sliced and given to a particular team unless the priority for that project is super high. Then you sort of get your hands on the latest and greatest machinery, but otherwise most of the times compute is always shared between teams. So it sort of you can sort of say, okay, I'm going to run my workloads at between 12 and 3. My workloads only take 3 hours, and the other team, if they are really good, they're like, okay, cool, it's fine. We'll run our workloads from 4 a.m. and whatnot. So there are different strategies that you can use in that particular aspect.
Hello. Yeah. So I know towards the end you mentioned that it's really important to kind of monitor everything, but like hypothetically, if there was like a company, like a small startup of sorts, if they weren't able to monitor that, would you say there's some sort of like hierarchy in terms of which of the optimization methods you mentioned they should focus on? Like, would you say there are some that are better than others?
So one thing that comes to mind is, when you have environments that are air-gapped, like gov cloud environments, right, where depending on your architecture, the workloads might be running within the gov cloud, but your control plane might be outside the gov cloud for whatever reason, then it is entirely possible that situation arises. In that case, you can either think about shipping a standalone solution for gov cloud, and you sort of integrate that into your into the paperwork that you sign with these particular special situations. But generally, from what I've seen in commercial clouds, there should not be a reason for companies to prevent metadata collection, which is essentially, because that's kind of what essentially this is. It's not really the data that your models are training on or your private data. It's pretty much metadata that can be used in order to surface more important information to reduce your cost, which I think everyone pretty much agrees is a good thing. So.
Okay. The second question, actually, this is more about just general broader trends in terms of like AI-related spending. I feel like lately I've noticed online there's a lot of people thinking that there's like a sort of perceived AI bubble between like NVIDIA, OpenAI, and AMD with some of their deals. I'm curious as to like what your thoughts are regarding some of that.
I think a lot of people who are much more knowledgeable than me have written and spoken about this, but there is definitely an arms race, if you were to sort of, or a gold rush. I think that's a better way to put it. There's definitely a gold rush with the perspective that NVIDIA is the only solution that can enable any and all players to sort of mine this mine data and convert them into Gen AI applications and whatnot. So I think there is a lot of the possibilities are infinite at this moment, and they just have not been tapped into yet. So I think it's quite early to say whether it's a bubble or whether it's not a bubble. But as I said, a lot of people who are much more knowledgeable than I am have already written and spoken about it. So I would just defer to them.
Thank you.
Hello. Yeah.
Hi.
So I just wanted to ask, when it comes to industry, what level of permissions and access levels should individual team should have on the computes? For example, if a team of data scientists want to run a high compute demanding workload, should they be allowed to create a new cluster by themselves and run it? And maybe after running the workload, they can delete off the cluster. And usually the process we follow is raise a request to platform team and they provision resources for us. Is that a good? But that is always time consuming. There's a trade-off involved in that. So I just want to know the balance between that and if at all any task comes up which is of utmost importance or high priority. So in that case, should they follow the standard approach of raising it to the platform team and ask them to provision resources and get back to them, or should they have the provision by themselves so that they can create their own compute?
Yeah, great question. So I've seen it happen both ways, and again, it comes down to cost versus value, right? So now assume that you're the core team behind that is building super intelligence at Meta. From what I've seen in reports, there is no dearth of funding for that particular team because hey, we definitely need AGI tomorrow, right? I would imagine in that circumstance, and of course, there's also a bit of trust involved here. The axis, I would say, is between trust and funding. If you've hired smart people, then you sort of assume that they know what they're doing, and you don't sort of babysit them. But on the other side, teams that have limited budget, it makes sense to for compute admins to sort of work really closely with those teams to understand what is it that they really need. Because you can come up and say, hey, I need 8 H100s for every member in my team. That's not going to appear out of thin air. There's a bunch of money that is involved in order to make that appear. So why do you need that, and what is it that you're really trying to do? That conversation can make sure that the value that gets produced at the end of the day is commensurate with the cost that you're sinking into the project. So I think there is no right or wrong answer to this. It generally comes down to what is it that you're working on, what is the value that you're going to produce, or what is it that you can show that you're going to produce if you were given infinite money, infinite resources, what is it that you can produce? And if there's a huge buy-in, hey, by all means.
So a lot of these cost spend optimizations and kind of resource provisioning considerations feel like they're pretty agnostic towards the resource, like whether that's CPU or GPU. So what are some of the unique considerations when you're working with GPU resources?
Yeah, good question. The first consideration is the fact that the dollar amounts that you can potentially spend on a GPU is of orders of magnitude higher. Like if you consider an M5 12XL or M5 16XL or even M5 24XL machine, that is like what? Like $2, $5 an hour. You consider a G5 48XL and you leave it running over you bring it up on a Friday and you leave it running over the weekend. It's going to bump up your cloud bill considerably. So that is like one of the core things. The other issue is most teams, when they start off using GPUs, they are like, hey, listen, I have a cost consideration, so I'm going to try to bring up spot instances instead of on-demand instances. And at least in let's say GCP or AWS, it is not necessary that you really get a spot instance available to you. Even if AWS had it, they're not going to make it available to you. Like, why would they ask for pennies on the dollar if they can get there's so much demand for these particular exotic GPU instances? Why would they give you? Why would they give those to you for free, almost free? So, and of course, in enterprise, you're not the only team that requires hardware. Like there are teams that are doing pre-training, there are teams that are doing data engineering, there are teams that are just doing ETLs, and all of them do require hardware, and cost is always a limiting factor. So. Every time there are new teams that are joining platforms where they want to run workloads, at the end of the day, most likely cost is going to be one of the core considerations. As I was mentioning to another gentleman, you always work with other teams to say, okay, you don't really run your workload utilization of resources is not 100% 24 hours a day. So okay, I'm happy to give you compute like from 7 a.m. to 7 p.m., but after that, 7 p.m. to 9 p.m., can I have your compute? Like, Do you have an issue if I use that? So it kind of always works like a hand in glove with a limiting factor of cost. I guess that's it. Yeah, awesome. Thank you all for listening.